In this video, we will explore IUPAC nomenclature and learn some of the basic naming conventions for organic compounds. This molecule, lactic acid, has the IUPAC name 2-hydroxypropanoic acid. Here's a helpful analogy to get us started with IUPAC nomenclature, using this molecule as an example. If, after completing my undergraduate studies, I were to pursue medical school, upon graduation, my full professional title would be Dr. Daniel O. MD. Organic compounds follow a similar naming pattern. The prefix is the substituent. The first name is the carbon chain number, which refers to the number of carbons in the parent chain, or the longest continuous chain of carbons in the molecule. The last name is the type of chain, and the suffix is the highest priority functional group. Applying this analogy to the IUPAC name of lactic acid, 2-hydroxy indicates a OH substituent is attached to carbon 2 of the parent chain. This part of the name corresponds to the title doctor in the name analogy. Prop indicates the identity of the parent chain being 3 carbons long, and ane indicates that we're working with an alkane. These parts correspond to my first and last name in the analogy. Finally, oic acid identifies the highest priority functional group, which in the case of lactic acid is the carboxylic acid group. This last part corresponds to the suffix MD in the analogy. It's a good idea to count the number of carbon atoms after identifying your parent chain. Place your pencil at the start of the molecule and trace over every connected carbon without lifting your pencil. If you have to lift your pencil at any point to reach another carbon in the molecule, it isn't part of the parent chain. Once you've done that, you can now assign it its name. Here is a table with the terms we use to describe parent chain length. Parent chains can be longer than 10 carbons long, but most of the carbon chains you will encounter are covered in this table. As we've seen a couple of times, the type of chain or the molecule's last name falls into one of the 3 categories: alkanes, alkenes, and alkynes. Alkanes have the suffix ane, alkenes have the suffix ene, and alkynes have the suffix yne. When naming molecules containing pi bonds, it's important to have a way to identify where the pi bond is in the molecule. To do this, we follow 2 rules. 1, number the chain from both directions, and 2, designate the pi bond as the lower of the 2 numbers that land on the pi bond. Let's look at some examples. Molecule A has no pi bonds. If we number the chain from left to right or right to left, we count a total of 4 carbons. A 4-carbon parent chain is given the first name but, and the alkane has the last name ane. Hence, this molecule is butane, or more specifically N-butane. Molecule B has 1 pi bond. Numbering the chain from both directions, we again count a total of 4 carbons. The pi bond is in the middle of the alkene and is on carbon 2 when we count from either side. Moreover, the methyl substituents are on opposite sides of the double bond. Therefore, we call the double bond trans. Altogether, molecule B is called trans-but-2-ene or trans-2-butene. Both are acceptable naming conventions, and you can use the one that sounds better to you. Finally, molecule C has 2 pi bonds. Numbering the chain from both directions, we again count a total of 4 carbons in the chain. We've seen before that alkynes can be either terminal or internal, and in this case we have a terminal alkyne where the C-C triple bond is between carbons 1 and 2. As a result, we call molecule C1-butyne or but-1-wyne. This molecule also has the trivial name ethylacetylene. Let's move on to naming substituents. Some common substituents we often encounter are halogens and carbon-containing groups, such as alkyl chains or phenyl rings. When naming halogen substituents such as F, Cl, Br, and I, we replace the ending of the halogen name with O. F becomes fluoro, Cl becomes chloro, Br becomes bromo, and I becomes iodo. For example, 2-bromobutane. For alkyl substituents, simple carbon branches obey the same naming rules as parent chains. First, we count the number of carbons in the branch and then use the ending YL to imply that the group is a substituent. For example, a 1-carbon substituent is called a methyl group, and a 2-carbon substituent is called an ethyl group. For example, 2-ethyl-3-methylpentane. Methyl and ethyl substituents are short and do not have any branched isomers. We can also abbreviate methyl as me and ethyl as ET. A propyl group has a single isomer, which we call an isopropyl group. When a 3-carbon substituent is connected in a line, we refer to this as propyl. However, if the 3-carbon substituent is connected to the parent chain at the 2nd carbon, we call it isopropyl. A butyl group has 4 isomers, N-butyl, sec-butyl, isobutyl, and tert-butyl. The N-butyl group describes an unbranched four-carbon chain bonded to the parent chain at the first carbon. The sec-butyl group has all four carbons still in a row, except the chain is bonded to the parent chain at the second carbon. The isobutyl group consists of an isopropyl group bonded to an additional carbon atom, forming a four-carbon group that is attached to the parent chain. The tert-butyl group has three methyl groups attached to a central carbon atom, which is also connected to the parent chain. Let's quickly discuss the four possible bonding patterns for alkyl carbons in hydrocarbons. Primary carbons are carbons bonded to one other carbon and three hydrogens. Secondary carbons are carbons bonded to two other carbons and two hydrogens. Tertiary carbons are carbons bonded to three other carbons and one hydrogen. Finally, quaternary carbons are carbons bonded to four other carbons and no hydrogens. This classification applies only to sp3 hybridized carbons, those involved in single bonds. It does not apply to pi-bonded carbons, such as those in alkenes, vinyl carbons, or carbonyl groups, carbonyl carbons. We'll do some practice identifying carbons as primary, secondary, tertiary, or quaternary at the end of the video. You may be wondering now, when is a group considered a substituent versus a functional group? Functional groups have a priority list. Let's refer back to our first example, 2-hydroxypropanoic acid. This compound has two major functional groups, an alcohol, OH, and a carboxylic acid, COOH. The carboxylic acid functional group has a higher priority than the alcohol functional group. As a result, we refer to the hydroxyl group as a substituent, hence the name 2-hydroxypropanoic acid. In summary, here's a table listing common functional groups and their priorities. The groups in the subordinate table have no difference in terms of priority, and instead they are usually listed alphabetically. When we want to indicate multiple of the same substituents in a molecule, we can use the prefixes di, tri, tetra, and penta for situations where the same substituent shows up 2, 3, 4, or 5 times. Now we can put it all together and name this molecule. Let's first identify the parent chain and type of chain. 6 carbons in parent chain for hex. Fully saturated chain for ane. Now let's take note of our substituents. 1 chlorine substituent on C2 for 2-chloro, 2 fluorine substituents on C3 and C4 for 3,4-difluoro, 1 methyl substituent on C5 for 5-methyl. Finally, we give the molecule a suffix, alcohol group on C1 for 1-ol. We can put the substituents in alphabetical order to give us 2-chloro-3,4-difluoro-5-methylhexanol. It's important to note that we use commas to separate numbers and dashes to separate numbers from letters. There are no spaces in a molecule's IUPAC name. Lastly, for cyclic compounds, we add the prefix cyclo before the parent chain name. For example, cyclopentane is a cyclic 5-membered hydrocarbon. When counting substituents on cyclic compounds, the initial substituent or functional group attached defines carbon 1 of the ring. For example, we refer to this structure as cyclopentanone rather than 1-cyclopentanone or cyclopentan-1-one. The ketone functional group marks carbon 1. So what if we have 2 substituents? The same rules apply. We refer to this structure as 2-bromocyclopentanone, where carbon 1 is defined by the ketone functional group and the bromine substituent is at carbon 2. As always, let's do some practice. Label the carbons corresponding to the following letters, A through G, in cholesterol as primary, secondary, tertiary, or quaternary. Feel free to pause the video and try this problem on your own first. Carbon A is bonded to one other carbon and 3 hydrogens, so it's a primary carbon. Carbon B is bonded to 2 other carbons and 2 hydrogens, so it's a secondary carbon. Carbon C is similar to carbon B. It is bonded to 2 other carbons and 2 hydrogens, so it's a secondary carbon as well. Carbon D is bonded to only other carbons, so it is a quaternary carbon. Carbon E is bonded to 3 other carbons and 1 hydrogen, so it is a tertiary carbon. Carbon F is bonded to 3 other carbons and no hydrogens. This one's a trick question because the carbon center is sp2 hybridized, and this nomenclature only applies to sp3 hybridized carbon centers. Finally, carbon G is bonded to 2 carbons, a hydrogen and a hydroxyl group. Because the hydroxyl group takes the place of a hydrogen, making this a secondary carbon, we call this a secondary alcohol. Let's move on to the next question. Provide the IUPAC names of each of the following compounds. Feel free to pause the video and try these problems on your own first. As always, we first identify the parent chain and type of chain. There are 5 carbons in the parent chain for pent, and we have a fully saturated chain for ane. Now let's note our substituents. We have 2 methyl substituents in the molecule at carbons 2 and 3, giving us 2,3-dimethyl. We don't have any functional groups in the molecule, so we end up with the name 2,3-dimethylpentane. In this next molecule, you might notice an isomer of butane, more specifically tert-butyl alcohol. Adding the suffix -ol for the alcohol group gives us the molecule's name tert-butanol. In the next molecule, we're working with a ring structure as the parent chain. There are 6 carbons in the ring for hex, and although we have a ring, we still use the suffix -ane in this case. Lastly, we add the prefix cyclo in front of hexane to give us cyclohexane. Now we can look at our substituents. We have 2 methyl substituents on carbons 1 and 2 of the ring, giving us 1,2-dimethyl. However, they have opposite stereochemistry, with one methyl group on a wedge pointing towards us and the other on a dash pointing away from us. Because these groups are pointing in opposite directions, we call it trans, giving us the final molecule name trans 1,2-dimethyl cyclohexane. If the methyl groups were pointing in the same direction, we would call them cis. Again, let's begin with identifying the parent chain and the type of chain. In this molecule, we have a 6-carbon parent chain for hex, and we have a fully saturated chain for ane. Because we have multiple functional groups / substituents in this molecule, we need to check which group takes priority. The ketone functional group has the highest priority, and because it is on carbon 3, our molecule has the suffix 3-one. With our priorities assigned, the other 2 functional groups are considered substituents and are ordered alphabetically. 4-bromo for a bromine on the 4th carbon, and 5-hydroxy for a hydroxyl group on the 5th carbon. Putting it all together, we get the molecule's name, 4-bromo 5-hydroxyhexane 3-one, or 4-bromo 5-hydroxy 3-hexanone. Now we're transitioning to some more challenging examples. Feel free to try these on your own as well before we work through them together. As usual, we start by identifying our parent chain. There are 3 carbons in our parent chain for prop, and we have a fully saturated chain for ane. Again, we have multiple functional groups / substituents in the molecule, so we need to assign priority. The carboxylic acid group has the highest priority, giving the molecule the suffix -ic acid. The remaining 2 bromines and phenyl ring are considered substituents, and we name them just like we always have. 2 bromines on carbons 2 and 3 for 2,3-dibromo, and a phenyl ring on carbon 3 for 3-phenyl. Finally, we just alphabetize the substituents, giving us the molecule's name 2,3-dibromo 3-phenyl propanoic acid. We start again by identifying the parent chain. There are 5 carbons in a ring in our parent chain, giving us a base name of cyclopentane. Once again, we have multiple functional groups / substituents in the molecule, so we need to assign priority. The 2 alcohol functional groups take priority over the alkyl substituent, giving this molecule the suffix -diol for the 2 alcohol groups. In this molecule, we have an interesting alkyl substituent. A 3-membered hydrocarbon ring, or a cyclopropane ring, is attached to the main cyclopentane ring as a substituent. In this case, we refer to this substituent as a cyclopropyl group. Recall that for ring structures, the highest priority substituent marks carbon 1 of the ring. In this molecule, we have a tie for the highest priority substituent with the 2 hydroxyl groups, so either carbon bearing a hydroxyl group can be considered carbon 1. However, we have the cyclopropyl group as a marker. If the hydroxyl group in between the 2 other groups marked carbon 1, then we would have the cyclopropyl group on carbon 5, giving us the name 5-cyclopropyl 1,2-cyclopentane-diol. Remember, we want to assign the lowest number possible for each group, so the hydroxyl group to the far left would mark carbon 1 in this molecule, giving us the molecule's name 3-cyclopropyl 1,2-cyclopentane-diol. Let's walk through these steps one last time for our final example. The parent chain has 8 carbons and is an alkane, giving us the molecule's base name octane. This molecule has 4 functional groups / substituents, an ethyl group, 2 chlorines, and an aldehyde group. Among these four, the aldehyde takes priority, giving us the suffix -ol. Counting from both sides of the parent chain, we find that numbering the carbons 1 through 8 from right to left gives each of the substituents the lowest possible number, which is what we want. This gives us the suffix 1-ol for the aldehyde at carbon 1 and 3,4-dichloro and 4-ethyl for our other substituents. Finally, we alphabetize the substituents, putting chlorine before ethyl because C comes before E. Altogether, this gives us the molecule's name, 3,4-dichloro 4-ethyloctanol. As always, thank you for watching, and I'll see you next time.